Joaquín Moraga from Princeton University, who's going to talk about Coregularity of Fano varieties.
Well, thanks a lot. It's a pleasure to be here and have the opportunity to speak in this conference. I met Professor Figueroa 3 years ago, not 4 years. But I have to say that the influence of his math actually started really early in his 19th. So today I want to talk about an invariant of Fano varieties or Introduccin varieties that I've been looking at, and I want to explain how did I get to this invariant. Although this invariant has been in literature for longer, I think it was not explicitly stated. So first, let me start talking about word complexes. So we have E, the reduced variant divisor, which simply normal crossing support on a projective on a normal variety S, normal projective X. Then we can associate with a CW complex that we call the word complex with another by DE. So whose cells of dimension K correspond to irreducible components of the intersection of J in J E J with the size of J equals to K plus 1. Okay, so essentially you look at it. The way that I explained it works, right? Every divisor corresponds to a point, intersections of two divisors will correspond to lines, and then you keep filling these to a CW complex. Okay?
These intersections are at non-singular points of X.
Yeah, let's say that it's simple normal crossing, and this is a
Each complex.
Okay. I don't think we need to smooth. We just need to smooth around the strata of theta. Let us see.
Okay.
So if X beta is a local Calabi-Yau curve, so let me mention that for me, local Calabi-Yau also always means canonical. So I want to say it now. And y will be a DLT modification. So let me just say in word what a DLT modification is. It's essentially a transformation, bidirectional transformation of XB, which now makes your local canonical sentence look like hyperplanes. You know, so for instance, if you have the cone over an elliptic curve, you have this point that is a local canonical center, but this doesn't look like a hyperplane or intersection of hyperplanes in this cone. But if you blow up the maximum ideal of the cone, right, there is a unique local canonical center that excites more to the elliptic curve. So it looks like a hyperplane inside the vertex. Okay, so you make any DLT modification, and with the following, the dual complex of the local Calabi-Yau curve to be the dual complex of the round down of this dy. And here, when I say that y dy is a DLT modification, let me be more precise. So you have pi from y to x, and then you define dy by this formula, you just put back to x plus b, and you obtain y plus b. I will give some example in a couple of minutes. Okay.
It's better to state this multiplicity once, because if it has negative coefficient.
Oh, and for me, local Calabi-Yau means B has positive coefficients, and then we only extract.
When you have DLT, it may have negative.
No, because my local Calabi-Yau.
DLT.
Okay, so of course the definition depends on the choice of the DLT modification, but by the work of the Fernando and Xu, it is proved that if you pick two different DLT modifications, you can go from one to the other using collapses, like DL collapses. And
it was already established in my paper.
Yes, it's also proving a bit by Professor Shukura, but I think it's up to the MFP at that point, right? Up to the MFP, maybe lower dimensions. So now we can define the Coregularity, which actually we can define for any normal variety. So if X is a normal projective variety, we can define well, first we will define the regularity of X, and we'll denote great X. So it will be the maximum of the dimension of the dual complex such that XB is local Calabi-Yau. Okay, so in the set, if this set is empty, so if the set is empty, yes.
I would like to say, so in my paper, I do not use DLT. I use any log resolution.
Right.
The same complex.
Right.
But then I do not need any MMP or something.
Okay, yeah, that's the point.
Much more general result.
Yes, yes.
Different next.
So then we say that the regularity effect is just because it says like there's no Calabi-Yau structure, so you know it's like the trivial case. So if the dual complex is empty, so if D and C is empty for every B, so there's no Calabi-Yau centers, I will set the dimension dual complex. Well, for me, if you don't like this, is just some nice counting something. And otherwise, if we're not in the previous cases, one can prove that the regularity of X will belong to 0 up to n-1, where n is the dimension of X. So finite regularity just means that you have a locality structure, and then if you have a larger regularity, it means that you have a larger dual complex that you can put inside your Fano variety. Okay? But I like this other invariant better. So the coregularity will be just the following number is just the dimension of X minus the regularity of X minus 1. And one can observe that the coregularity of X and n-dimensional non-variety is always in the interval negative infinite, that this just means you are not Calabi-Yau, 0, 1, all the way to n. So if you want a better explanation for the coregularities, essentially you look at all the possible complements, you take the DLT modifications, and you look at the dimension of the minimal of canonical set. Okay, this is that phrase was for the experts. So let me mention something. If we look at varieties of maximal coregularity, so Fanos of maximal coregularity, we don't have many examples of those. So this is the ones that I think Professor Seguro will have another people call exceptional Fanos. So if the coregularity is equal to the dimension, these are called exceptional, and we have a really nice theory about them, you know, abstract theory. We know that they form bounded families. They form bounded families by the work of Picard, and we know they're asymmetric stable. So all these nice theories that we have about Fano sort of trivialize in the exceptional case. But the problem is that we don't have many examples, right? I mean, I don't know anyone that can do like huge families of exceptional Fano. So
that's coregularity from n implies
so sorry, from now on I will restrict to the Fano case, okay, just for this. So from now on, let's start.
So can you repeat the coregularity means that the highest dimension of the local center you can construct with the Calabi-Yau structure?
Yes, exactly. That's the thing. So, but here we don't have no many examples, right? On the other hand, if we look at the regularity of X equals 0, I can give you a ton of examples. All toric varieties, many deformations of toric varieties, many diversion models of toric varieties have coregularity 0, right? So here the big two reverses, right? So too many examples, right? But the problem is that we don't have a general theory or a general framework. So no general framework. So there are no general terms that we can prove for coregularity 0 Fano variety. Okay, and then well, the aim of this talk is to start a conjecture that will give a general framework of how to maybe understand a little bit better the coregularity 0 Fano varieties.
And also a remark about this exception. In surface cases, one of my students, Abba, he wrote, but never published me, 2 or 3 preprints about surfaces. He uses hundreds of examples.
Oh, wow. Well, then maybe it will be published.
No, but it was not checked. No. For some gaps.
I see.
But it seems to me 90% it's correct.
Okay.
I know some people try to rework his paper, but it's still quite old.
Okay, so let me try to convince you from now on. But well, let me just mention that it seems for me that much of the obstruction to be basically stable and to be bounded somehow is hidden in these dual complexes. So what my proposal is that we should study these dual complexes in a way more deep way, in a way more structural way, to try to see what can actually prove statements of the time. If the dual complex, the possible dual complex have this sort of shape, then we have to get instability or bounded families. But let me just say that just looking at the dual complex won't be enough. Okay, so now my next goal is to convince you that most Fanos have coregularity 0. And of course, most, as usual, algebraic geometry doesn't mean much. Right? Because you can have models where no Fano has coregularity 0, but let's look at the classical examples, or some classical examples and not very classical examples. Okay, so if you look at five equations of the projective space, you get Fano varieties or log Fano varieties. And if you assume that the quotient is exceptional, and then you give an upper bound for the log discrepancy, then you get only finally many samples. So only finally many in each dimension. If exceptional plus log discrepancy bounded away from 0. Like you got an epsilon larger than 0. So you see, and of course, if you take like any abelian group, you get something for coregularity 0. So there are way more coregularity 0 than exceptions. And let's look at Duval's similarity. So sorry, here I will do like a big jump. One can take the same definition that I gave for the Fanos and Calabi-Yau and do the similar definition for PLP and canonical. James? Sorry? G is finding.
Finding group, it's always fun. No. Exceptional, very rare case.
No,
Exceptional groups.
Because G can be any group, right? So you get all the way to Sorry? No, this line was to convince you that there are no many exceptions among quotients of projective.
It responds to exceptional groups.
No, there are only finally many examples.
Yeah, fine.
In each dimension, if you say exceptional, not discoveries larger than some bound. Is that the fact? And this is proved by Coregularity. It's inside one of his papers.
So you're not fixing it.
Okay, let's fix it.
M fixed in F.
Okay, so I don't want to make a statement. Okay, so if you look at the N of the singularities, or if you look at the Duval singularities, the N and the N have coregularity 1. No, so this one has coregularity 0, and this one has coregularity 1. Okay? Let me give you more. Now let me give you a couple of propositions that are sort of propositions that compare coregularity 0 with toric things. So the first, well, I go through these propositions, but actually it's a good exercise. So proposition 1, if X is a Fano surface of coregularity 0, then you can find a boundary that exists B such that XB is log Calabi-Yau, and a 2-to-1 cover from XB and 2-1 cover to Y comma BY such that Y comma BY and I use such that once and Y comma BY is log Crevant. Sorry. So actually it's log Crevant with projective space width. So Crevant to, let's say, P2 L1 plus L2 plus L2. So essentially, Fano type surfaces of coregularity 0, you can correlate them to toric things by doing natural things in the minimal model program, by taking covers and running some minimal model program. So what about other examples? So if you like toric geometry, the next to toric geometry case, which is not toric, is what we call complexity 1 variety. The complexity 1 variety is an n-dimensional variety with an action of a GMN minus 1 torus, so a torus of dimension n minus 1, which acts effectively. So what can we say about complexity 1 of coregularity 0 proposition X Fano type of complexity 1 and coregularity 0? Then there exists B larger equal to 0 equivariant such that XB is log canonical. Sorry, it's log Calabi-Yau again, I assume that the is canonical. A 2-to-1 cover has been 2-to-1 right, such that, and now you are guessing is by rational authority, such that y is forms to authority. So these varieties that are the closest to toric but are not toric, if you post the condition of probability 0, you can again make the toric somehow. Like deformations are also very usual in the minimal model program and in rational geometry. But let me mention that Esparti and Sophie Calabi-Yau and maybe some other people have examples, right, that of locality of pairs of dimension 3 whose dual complex is a sphere and they're not very rational to something toric. In their examples, you can actually degenerate to something of complexity 1, that they are to 1 cover, and then degenerate to something toric again. So I'm not claiming that you can actually make everything of Coregularity 0 toric by taking covers, running them and doing deformations, but it would be super interesting to find an example in which there is no way to turn it into something toric, doing deformations, covers, and energies. Okay, are there any questions so far?
So I guess your definition for regularity is wrong.
Why?
Because that actually complicates regularity. I mean, regularity, you only care about the dual complex of the pair itself, rather than taking account.
I agree with you that there is a definition of regularity in the literature. Mine should be called absolute regularity or something like
And it's
this.
not complete regularity.
For simplicity, let's say regularity. Okay.
And what means complexity? Complexity.
Oh, that's a very good question. I think there is an inequality relating complexity for regularity, but I haven't been able to do it yet. Okay, so let's keep going. I lost the third page. Okay. So let's well, if you look at the pesos too, all the pesos that don't have degree 1 have Coregularity 0, the pesos degree 1 has Coregularity 1. So here, I mean, okay, I guess that all of you should be convinced now that most Fanos have Coregularity 0. This means nothing. But if we get a good conjectural theorem for Coregularity 0 Fanos, we'll understand things a bit better. Okay, so now let me tell you one of the reasons why I started looking at the Coregularity. So I was trying to answer this question. So take a rational number, find the minimum n, such that there exists, such that Q is a n-dimensional canonical test. So I was playing with this just for fun, I didn't think that there was any deep theory behind, and it's super hard. and the worst part is that I tried many examples and I actually was getting the same mechanical test. So I was increasing the dimension, and I was getting the same mechanical test as before. So then I started thinking, okay, maybe there is an invariant that measures something like localized interactions better than the dimension. And then I took the resolution of this guy, I tried to, and I realized I have really small canonical centers. So then I came up with the conjecture that if you have really small canonical centers, then you can prove ACC without the bound on the dimension. So then we came up with the following definition. So SCP, I will write correctly by C, Ij, it will be the set of L, such that L is a local threshold of X delta with respect to gamma. The coregularity, when you hit the local threshold, the coregularity is at most C, and the coefficients of delta are in I, and the coefficients of gamma are in J. Okay? So essentially, are all the local thresholds that you can produce with bounded coregularity.
What if you later on coregularity? You only define that for an animal, right? And now again, for this definition, you only care about the dual complex rather than the dual complex of a complex.
Okay, so you can do two things. You define it locally, and that's what we do. And then if we're not in the local picture, we ask that for every minimal local center, the coregularity is the right. Okay, so sorry, I was hiding this a little bit behind it. Of course, most people that look at this study will think about the local setting needed. Okay, so let me tell you one of the main terms that I want to discuss today. Okay, so this term is due to Fernando Figueroa, and Princeton, Junyao Peng, which is another recently, 2022, the term is the following. Let ij be two sets satisfying the DCC. In CO1 satisfying the DCC. C a positive integer. Then low canonical thresholds of co-regularity bounded by C with coefficients in J satisfies. So see that this is a dimension-free generalization of Heiko-McKenna-C paper on low canonical thresholds. Okay, so let me tell you that the proof actually factors, as the experts may expect, through the global statement. So I will write the global statement, and then I will give a very pictorial proof. I don't want to, swamp you in details of minimal model properties. But at least I want to give you some sort of pictorial. So the global statement is the following. So let I be a set in 0, 1 satisfying CC. C a positive integer. Let X be a local Calabi-Yau pair such that the two following conditions hold. One, the coefficients of B are contained in the set I, and two, the co-regularity of XB are almost C. Then the coefficients of B belong to this belong to a fixed, or finite subset. I know inside. Okay, so let me give you like some sort of pictorial argument. I'm pretty sure the expert will sort of see this here. So Heiko-McKenna should look this if you fix the dimension, right? So what is the natural thing to do? You try to go to the DLT modification and then try to do a junction to one of the components and cut the dimension one each time until you get to a sequence of varieties of bounded dimension. So let me try to convince you with a picture. So let's say that we have a sequence violating the statement. So the co-regularity is bounded, but the coefficients violate the same condition. Sorry, am I saying things right here? Yes. So sorry, violating the descending tree. Is the statement right? I'm asking because I always leave ACC with DCC, sir.
No, that's very true.
Yeah. No, I was just asking because I always, stop ACC with DCC. So that's what I mean. Okay, so we start looking at X1, B1, X2, B2, and so on. I think I should say ACC here, right?
What's that equation? That's
DCC.
But to get a finite set.
yes, I mean that's the global thing. The global thing is that DCC is plus one.
Yeah, so I knew that.
No. DCC is correct. DCC is correct. ACC is wrong.
Oh, sorry.
DCC.
I knew that I always get this. Okay, so the proof is the following. You take a sequence of Calabi-Yau with increasing dimension. Okay, and for each of them, you need a coefficient, D1, D2, inside D1, D2, Dn, such that the coefficient of di, that I will put di, is not in a finite set. And what you want to do is to perform a junction to one of the components of coefficient 1, right? If you can do that, then you will draw that sequence like in going up because the dimension is going up. And then if you were able to perform a junction to a component, then you should be able to reduce the statement to lower dimensions. But here one has to be quite careful because you don't want to, in each variety, you will have to cut down more times, right? Because we're assuming that the dimension is divergent. So essentially what we do, so imagine that we have a lot of components with coefficient 1, and I just pick one, S. right? And then I have this chosen component di, whose coefficient is nothing about. So I will run against kxi plus vi plus epsilon si MMP. So this MMP is always si positive, and the flip curve or contract curve will be, well, the contract curve doesn't exist anymore, but the flip curve will be si negative. So this is like sorting everything inside si. So when this MMP terminates, the chosen di will actually intersect si. So we can perform a junction and take all these varieties and drop the dimension by 1. So I have to say that something you can just drop the dimension all the way to 1, but at least you will get a new x to 1, b to 1, you will have an xn1, bn1, such that there is still some coefficients that is violating infiniteness, but you got the dimension. And then the rest of the proof is keeping track of this process and proving that if you can flush down all the varieties down to the dimension, then you are still violating the finiteness of the coefficient. And then we just apply mechanics in the usual way. Okay, sorry for the.
Joaquín, in certain sense, you were right about ACC. It means that when you prove this result, it's more natural to prove it's not only DCC, but if you have real coefficients, they also ACC. So you have DCC and NCC, the finite set.
Yes, yes.
This is in my paper, it's one of my last different example.
Okay, so now that we learned this connection between coregularity and parameter, so let me tell you my expectation, which I'm sort of borrowing a conjecture by Coregularity, to make like a sort of classification, or well, not classification, but some sort of nice statement, conjectural about coregularity 0 Fano varieties. So the conjecture is the following. I'll tell it here. So there is a structural conjecture for coregularity 0 Fano varieties. So the conjecture is the following. If X is Fano of coregularity 0, then we can find a 2 complement. We can find E in negative 2dx such that X, B half is log canonical and there exists a Fano cover that gives the Calabi-Yau structure. So let's say, well, I'm not bounding the index, but the idea is that when you discover, you still get a Calabi-Yau, and the word complex now is just a tree. So the last part of the conjecture is just a conjecture by Professor Coleridge and Manchu. But the rest of the conjecture is new. It's very similar to, I think, this expectation that Neff-length bundles on smooth of Neff-Tartini dice on smooth varieties are effective. It's sort of pointing in some point in that direction. But I want to say that if you have something toric, right, has coregularity 0, and then the ideal situation is that we prove the opposite, which is not quite the opposite, but the closest to the opposite, that if you have coregularity 0, then you're sort of very close to be something that looks quite much toric. Okay? So
I think it's also true for Fano type.
Exactly, actually I should say Fano type, or even Calabi-Yau coregularity 0. You can always
No. If you consider Calabi-Yau in general, local, it may
No,
have too many rational curves.
No, but Coleridge and Shu prove that if you have coregularity 0, you can always partially transform Fano. So we follow again in Fano coregularity 0. So let me tell you what I would like to do next. So like a goal for which probably we're gonna start working on this already in dimension 3. So you know that for toric varieties you have fans, right? And this sort of recovers the whole isomorphism class of the projective toric varieties. So one thing I would like to do in the future is enrich the dual complex to a fan dual complex. So for a coregularity 0 Fano variety to a fan-like dual complex. Let's call it gamma sigma xv, although it's not defined. So what will be the idea is that, you know, what is the fan of a toric variety telling you? The fan of a toric variety is telling you the normal bundles between the strata, essentially. If you know the normal bundles among the strata, you can recover the whole toric fan. If you know the toric fan, you can recover the whole, all the normal bundles of all the toric strata inside toric strata. So what I would like to do some sort of extra structure inside the dual complex such that now it looks like a fan. I don't hope that this will recover the isomorphism classes, but to compute invariant, it should be like a very good tool. So now let me mention that we have some theorem that goes towards the direction of this conjecture together with Mirko Mauri and Stefano Filipazzi. So what we're proving, so this is work in progress. And now I will use the language of general spheres. Sorry, if you're not familiar with this, but you can set m equals 0. So this is theorem. You do Filipazzi, Mauri, and speaker, work in progress. As is the form. If x b plus m is a generalized local Calabi-Yau pair of Coregularity 0, then twice the byte index of px plus b plus m is linear on the field of 0. So where that is the byte index of kx of b plus m. Okay, so let me actually mention that if you assume some nice conditions, this is already known by the work of Professor Pollard and Professor Hugh. So, but actually the nice conditions that you need to assume are quite too nice. So let me mention that if m equals 0, b is reduced, and the dual complex of SB and manifolds of agreement, right? We just know that it's a pseudo manifold. Then the sections of kx plus b, you can see them in Hn-1 of the dual complex. Right? So essentially this tells you that if the dual complex is orientable, then you have a section. If it's not orientable, then twice the kx plus b will have a section. Because any manifold have a 2-to-1 cover which is orientable. But in general, we just know that this guy is a pseudo manifold. And pseudo manifolds may not have 2-to-1 cover that are oriented. So this like induces a major problem. Okay, so let me just say that to tackle this term here, we try to follow Guittard and before Robert Shokuro theory of complements. But there is like well, let me tell you what the main issue is with trying to mimic these techniques. And let me tell you how we want to fix it. So, if you have read Professor Shokuro first term on complements, or lower the second term on complements, or we start with canonical systems from Fano varieties, you know that you can usually leave sections from the canonical bundle formula. So if you have x to z and x b log Calabi-Yau over c, then you can write kx plus b. This is phi equivalent to some lambda that you need to bound with some proof, and then you have Euler squares as well in the base. And what Kruger and Shokuro does is that if you can produce a complement for this guy, you get a complement for this guy. So what is the problem in the context of the theorems that I'm not bounding the dimension? So the dimension of my general fiber can be unbounded. And the dimension of the general fiber may not have Coregularity 0. So actually, there's no way to control the Coregularity. So we need to do a new twist in the proof to get the statement. And what we're doing is trying to, instead of pulling back the complement from the base, we do something that I like to call push pull of sections. So you have E inside X comma B, a component of coefficient 1 that dominates the base. So you can always, do some sort of MMP argument to get that at least one component of coefficient 1 will dominate the base, and then you are marking down to Z, BC plus AC. So what you would like to do is to lift the component from E. But in many cases, you don't have enough positivity to apply automata-period. You try to run all the possible MFPs and try to get a model in which there is enough positivity, and you go crazy, right? So instead, what you do is you do perform a junction to E, then push forward the complement to Z, and then pull it back using the canonical boundary formula, but never touching the coefficients of these two. Okay, so this is some sort of work in progress that we hope that it goes through, but it will give a new twist and a new little idea in the theory of complements. Okay, so now
as I told you, actually we use this fallback formula only for exception, usually for
Right.
special cases.
exactly.
For in general situation, when we have little bit perturbation of coefficients, we do not need this. We have very good theory of adjunction. We do not need this projection. And this is exactly an coregularity correspond. But when we have special cases, we need to worry about this.
Right. See, actually, Professor Shapuru, in his paper, Boundedness and Existence of Complements, his last paper in our chemistry, or maybe the previous one, he proved a case of this conjecture under some generality assumptions of the canonical system. Okay, so now let me tell you the second motivation why I started studying Coregularity of Fano or Calabi-Yau curves. So let me define the deformation Coregularity. I will bring to it here. I want to keep this conjecture up there. So essentially, the deformation Coregularity is the following. Deformation Coregularity of XE is the minimum Coregularity of X naught B naught, such that, okay, I guess you know what it's doing. There exists some flat P-Gorenstein family over A1, such that some general point is isomorphic to X comma B, and the central fiber, oh, sorry, I want to take the coregularity of the central fiber. And X naught B naught is just the central fiber. And here you may assume that you may allow the central fiber to be semi-canonical. So why I'm doing this is because, you know, people may say, oh, coregularity 0 seems to be a very specific case about Fano varieties. But actually, there is a lot of Calabi-Yaus that become deformed into coregularity 0 Fano varieties, like an elliptic. And well, there's a lot of examples in higher dimensions. And so now let me explain you the second reason why I got into trying to look at this coregularity. So one reason was the canonical thresholds. And the second reason is written in page 5. Okay, this was the one that was in my hands. Okay, so I discussed this problem a little bit with Portugal, that you know they have all these new examples, right? That in the usual, I have 10 minutes, right, or 2 minutes. 2 minutes, right? So they have all these examples, right? By the general theory, by Collar, McKernan, Haken, and many others, we can sort of bound invariance in terms of the dimension in the minimal curve. And then Cotaro came and said, well, with Renstau and Lisser and Chen-Siwan came and say, well, you know, these constants are huge, are down exponential of the dimension or something like this. And the problem is really simple to say. The problem is take a sequence, find a sequence of Calabi-Yau varieties Xn such that their index grows at least double exponential. Or, well, let's say it grows at least non-polynomial. Let's start with this. Okay, so I was trying to solve this problem, and I started to compute some examples, you know, things that are close to complete intersections inside toric varieties, because I have some hope that I could find an example there. But the problem is that I started looking at the index, and I was getting 1, 3, 4, 6, 1, 3, 4, 6, 1, 3, 4, 6. And I was like, okay, there is something going on, right? Or even I'm doing the computation wrong, but there is something deeper. So then I started trying to deform these Calabi-Yaus, and I realized that they all have deformation coregularity bound. But then you can bound the index of the central fiber, and then in many cases you can bound the index of the nearer fiber. So if you have sequences of Calabi-Yaus with bounded deformation coregularity, then the index will be bounded above, and I'm not getting the context. So if anyone knows how to solve this problem, I think it will be very great. So in the last 10 minutes, I just want to propose questions related to the coregularity. And sorry, some of them may be not super precise, but we can discuss it about this impact. So the first one is actually a question by Junyao. So I gave a talk somehow related to this in Princeton at the beginning of the fall semester, and we got this question afterwards. So in gauge stability theory, as we know that if you have a Fano variety, you can find a complement such that now the normalized volume is monomial in some DLT modification. So the first question, let me call it question 1, and then we have to do this example. Let X be a Fano variety or let X be Fano type of coregularity C. Can we find a complement computing the coregularity complement of coregularity equal to C such that the normalized volume is monomial in the DLT modification. So these are big connections with phase stability in some DLT modification of this component. Okay, and I think there might be some deeper connections. If one studies this fun-like dual complex, I suspect that one can actually maybe not compute the normalized volume, but get quite close to it. Yes. Yeah. Sorry, that's fine. I say that this file was going to
Minimum price should be related to this complex.
So let me mention one other thing is that so another topic in which I'm not much of an expert, but let me just list it. So we know a lot of Fanos in positive characteristics that don't lead to characteristic 0. None of those have coregularity 0. So maybe this too bold for conjecture, but maybe let me propose it as a question. Find Fanos with coregularity 0 that don't lead to characteristic 0. I mean, one could do some sort of heuristic argument, right? You have something of coregularity 0. If you're seeing this conjecture, it is sort of covered by this shell of devices of coregularity 0 that again looks like Fanos, and those you can leave by induction dimension. And then you have some possibility on the normal tangent, right? So maybe they all leave, but maybe I'm laughing too much. But let me ask you a question. To find examples of Fanos of coregularity 0, examples of Fanos of coregularity 0 over FP that only is positive to characteristic 0. If I remember well, all the samples in the literature we have don't have coregularity 0, unless I made the computation. So I think I still have 7 years. So okay, so with Ivan Kelsov, we were talking about phanography, right? Maybe it would be nice to add the line coregularity to the phanography and start trying to start this something canonical system from the perspective of the dual complex. So let me.
Only after.
Sorry.
Only after case study.
Okay. I see there's some curiosity here. So let me draw some pictures, right? I mean, it's good to lead the talk with a couple of pictures in mind, so I don't want to be busy. So let me tell you how the Fano of coregularity 0 looks in dimension 2 and 3. Once you have this conjectural complement. So if you have something, so if you have a Fano type of dimension 2, once you have, well, actually the conjecture, this conjecture is easy to prove in dimension 2. It's an easy exercise. In dimension 2, what you expect to see is the following. So you add this boundary, and then you will have a lot of devices in coefficient 1, and this is a red will mean coefficient 1/2. And then you will have this sequence of lines that are supposed to be intersecting each other with coefficient 1/2. Okay, now I won't write with 1/2 anymore to know that this sort of very orange red is 1. And then you can take a 2-to-1 color and you get something that is not 2-to-1 to something color. 1/1. Okay, so this is how a Fano of dimension 2 coregularity 0 looks like. And let me continue here. And actually, in dimension 3, we get a pretty similar picture. And actually, one can prove this, but there is not just a simple problem that needs to be proved. If you have a Fano type of dimension 3, and Coregularity 0, you get a similar picture. Why am I doing this? So this is half a sphere with some sort of polyhedral. And then you have this sort of, it looks like an egg, with coefficient 1/2. And you have two items. So it looks something like this. It should look the LP and then sorry. So 1/2. And then when you get a 2-1 cover, then you get a sphere. And then you have the sphere. And then you have this. Okay. And actually, I think it would be very nice if we take these classifications of Fano trifolds in dimension 3 and actually describe this sphere and which are the shells that we use them to get them. If you, sometimes when you describe for someone outside of the mechanics a Fano trifold, I don't know what to imagine, but if you tell them the surfaces and how they look, they make it a sort of nicer picture to bring home. So finally, let me do some speculation related to mirror symmetry in case that anyone is interested. So maybe I will just maybe let me pose it as a question because again, I think a lot of the last 10 minutes are quite conjectural. But if you have counterexamples, I think it would be actually valuable to compute counterexamples. So the mirror of a local Calabi-Yau trifold of Coregularity 0 has Coregularity 0. So what this means? It means that, well, in dimension 3 at least we can compute this. Well, maybe we cannot compute this. But in dimension 3 at least we can, I think it is doable to compute them. I don't think that it's known what PL structures we get on spheres for 3-dimensional local Calabi-Yau. But this is saying that you get some classes of PL structures on 2-dimensional spheres coming from 3-dimensional Calabi-Yaus. And if this conjecture is true, it's telling you that there is some sort of involution action on all the PL structures on the spheres that you can get on the Calabi-Yau. And I think this is quite interesting. Maybe it has some connection to something else, but I have to say that actually this question was asked to me by someone else. It's not my own.
Best to ask Katsak.
Yeah, maybe we should ask Katsak, right? I think I have 2 more minutes, but maybe it's a
Did you investigate these trifolds of index 2, with index 2 complements? On the question, for instance, is it finitely many surfaces up to birational transformation, birational Clippan transformation of index 2?
I suspect that's true. I don't have a proof yet, but I suspect that's true. Yes, I think that there is this example.
In one-dimensional case, we have this.
So I think
except for length, but I mean at the edge we have just 2 types.
Exactly. So there is this example by Spaldi, and I know 2 more examples that are not in the same birational up to finite power family.
Of course, in higher dimension, it's not true, but at least up to dimensions.
Yeah. So I have to say that I only know 3 different examples up to birational.
3 different examples.
But I don't know more. No, but there could be more. Like these are the ones that I could compute.
Could I ask something? I don't know if this is going to work.
Oh, so Professor Totaro wants to ask a question.
Sure. Okay. So if you can hear me, that's good. Yeah, I was just going to say that that Changxi Wang and Louis Esser and I, we did find those like Calabi-Yaus with index sort of doubly exponentially large, and we really actually meant to talk to you about this, Joaquín. So pretty soon.
Okay. So that's what he said, or maybe misunderstood? So one of the problems is solved. And he's going super fast.
Solution.
I guess we'll see. giving one of the papers.
Okay, I guess we can thank.
It's a big